Last meeting actually we covered the semiconductor basics and p-n junction devices. In this talk, I will try to elaborate and build the theory based upon the earlier topics presented, and I will introduce one more topic, that is metal semiconductor junction diode. That is Schottky diode we call it, because Schottky has given the theory of barrier lowering effect due to the metal and the electron present in front of metal in the semiconductor. Basically, image charge barrier lowering. Okay, just see my screen now.
Yes, sir.
Yes, sir. You can start.
Oh, oh, good. Thank you very much. It was some technical issue, so we are late by 24 minutes. No problem. Okay. The slides are visible completely, or part of that means it's a slideshow or not?
Completely visible, sir.
Okay, okay. Thank you, sir. So, shall we start now? So, in last meeting, actually, we completed this introduction about semiconductor crystal structures. We discussed how energy band diagrams are calculated and what is the behavior of the carriers, electron or holes, due to the different crystal lattices and the respective energy bands and diagrams because of their nature, actually. And we are using these the basic nature of the materials for the semiconductors to use in different devices and using different technologies. And then the topic was carrier transports, how carrier moves in this semiconductor, dot semiconductor and type P type bar and PN junction diode. And there is a trap related phenomena, that is Shockley-Ridal recombination and generation. And that is a very important topic when we study semiconductor physics and their particular application. It is the defects and traps and their SRH recombination and generation that dictates the final performance of that device. So after that, PN junction device was covered, and now I will start from here. I think some of the questions were asked about the crystal lattice and the functioning. And rest you can raise question today, and today I will try to cover the further section, and now it will be little bit advanced one. Earlier it was directly from the books, now it is from the research papers also. And today talk my talk will be based on metal semiconductor junction, because the metal semiconductor junction is the gate of MASFET, JFET, junction field effect transistor, metal semiconductor field effect transistor, and the high electron mobility transistor, that is HEMTs, which I will be discussing. And gate is the heart of the device, of the transistor. If we can control the gate performance, how it behaves, how is the leakage, how its capacitance is varying with the voltage and with the time and frequency, we can control the characteristic of that transistor. So in today's topic, I will cover one more measurement technique, that is deep level transient spectroscopy, DLTS. Actually, it's an electrical characterization tool, and we do it in our lab regularly. And that tells where is the trap is, what is the energy level, what is the capture cross section. That is from the transient measurements of the capacitance as well as current. So it's our wish in which device what we want to measure. Sometimes we do both. Sometimes it is not possible to measure the capacitance due to the higher leakage currents. Then we do only current measurements, transient current measurement. Then gallium arsenide HEMT, basic of gallium arsenide HEMT I will present, and it will be followed by gallium nitride HEMT. I will highlight what are the differences, and after that DC performance or the issues in these technologies, because see these technologies are around now 2.5 decade old, but still it is not at the level of maturity. So still there is no aluminum gallium nitride HEMT which can fly in space with reliable operation. So Still, gallium arsenide rules at space applications, high frequency, high power applications. So after that, I will present the some RF characteristic of gallium nitride HEMT and measurement setup which are being used in our lab. I will present brief introduction about them. So these are the references. And in addition to book, I will follow the publications. You can see the list of publication on my Google Scholar profile, and I will be using some of the view graphs from those research papers to introduce these particular topics. So, if you remember that in PN junction we have discussed when there is a p-type semiconductor and there is an n-type semiconductor, their Fermi level are not aligned when they are separate. But when we join metallurgically, there is a single Fermi level and band alignment takes place to maintain that single Fermi level or a chemical potential throughout that one device or one PN junction diode. Here there is a metal semiconductor diode, and to make a metal semiconductor diode on an N-type semiconductor, we need a metal which has a higher work function. Means it should have a higher electron affinity. It should attract the electron from the N-type semiconductor so that a depletion region is formed in the N-type semiconductor and a barrier will be formed, and the ideally that barrier height of this PN sorry metal semiconductor junction will be the difference in the work function of the and the electron affinity of the n-type semiconductor. And here thermionic emission, I have discussed that theory is applicable to calculate the currents this barrier. When we forward bias it, that barrier is reduced and more electrons can flow, and the forward diode current is exponentially related with the applied voltage, and in reverse bias, that is a leakage current, it's almost constant, but it's again related with the barrier of that metal semiconductor junction. So why we call it this as a Schottky diode also, because Schottky has given a theory, a particular theory, very important theory, that due to this image force barrier loading, because there are electron present in this n-type semiconductor, so there is an image uh, formation due to the metal interface present at that metal semiconductor. And when we see this Maxwell equation and their boundary condition, we can calculate that there is a image charge is there in the metal side, and a electron means electric field is generated that lowers the effective barrier at that metal semiconductor interface, and that is related with the dielectric constant of that semiconductor. That theory gave us that you will say that why the big deal that delta phi is very small. It's not so small because the currents are related exponentially with this delta phi. Any small change in this barrier height will drastically change your forward current, reverse current, lead current for the diode. Next is now apps. There are Excuse me for this network issue. My connection got
No, sir. No, sir. No, no problem, sir.
okay. So I was discussing about the interface states. Actually, it's a very important topic. And if you ask me, or if you talk to me, what is the single biggest challenge in the semiconductor technology? Is the interface state, and sometimes we call it as surface states. Actually, if you see anything, any surface, there is a discontinuity. The most prominent discontinuity of that material is at the surface, and that discontinuity of the material gives rise to energy state in the band gap. And whosoever mastered this semiconductor technologies has mastered these control of surface states or interface state. For example, if you see the history of semiconductor development, we have seen that people were trying to make MOSFET much before the BJT, but BJT came first and MOSFET came later. Later on, it progressed so much that it has overtaken everything. Most of the application, 99%, is silicon MOSFET in semiconductor electronics. But why it was happened? See, in BJT the design is inside the semiconductor layers, not at the surface. But in MOSFET, actually, that controllable gate is sitting on the insulator, and that make an interface with the semiconductor. And that interface states played a big role, and it was a big challenge to control this surface state to make that MOSFET working in a workable condition. That's why that invention was led by BJT, but anyhow, but the companies who has mastered these MOSFET technologies still they are number one in the world. You take the example of Intel or any other companies, they have mastered and they have controlled these interface states. Why I'm emphasizing on this here? Because this is the main challenge when a new person or new company try to build their transistor. They have to master this control of surface state. They should behave in a particular way to suit our application and on our wish. And the behavior of uncontrolled surface state is beyond explanation, and we try to characterize from many techniques. For example, we do XPS to study this what is the surface condition of a semiconductor, but practically what matters, what is the electrical characteristic. So we try to interpret the measurement data of capacitance, voltage, and the current voltage characteristics. But still, this is the topic of hot research because no one publish directly what they have done to control this. First is the environment. As the discussion in the last lecture also, that environment plays a big role, and the processing its steps, time itself, time between two steps, that plays a major role. But again, understanding also matters. So therefore, there are a lot of models, and they are specific to particular semiconductor material, and they are particular to particular fabrication technique. So they are particular to foundry itself. Means they are not applicable to other foundries. So that's why this topic is about research in semiconductor technology. So next is in a metal semiconductor diode, actually we need to make a gate in the transistor, and here to make the complete transistor, we need source and drain contact. So how we can make it? Ohmic contact. These are completely ohmic, and we control the conductivity between source and drain by controlling the electric field at the gate. So we do it by high doping. What what is the effect of high doping? As you have seen earlier, the depletion width is inversely proportional with the doping. When you increase the doping, the depletion width reduces, and when a doping is so high, it is in the degenerate or very high, in 10 to the power 19 per centimeter cube atoms of dopants are present, then a tunneling phenomena takes place, and tunneling is bidirectional. there is no diode now. It behaves like a ohmic contact. So this is the method we use to make a ohmic contacts for source and drain in our transistors. So now next topic I will present DLTS. So deep level transient spectroscopy.
Excuse me, sir.
Yeah.
Sir, your screen is not present. Sir, please try to present your screen.
Oh, sorry.
Okay, sir. Thank you.
Now it is present.
Yes, sir.
Oh, so means you have missed this one also. This one
Yes,
was
sir. Yes.
for, yeah, this one was for ohmic contact, which I
Okay,
was
sir.
talking about, and
Yes, sir.
now this is a DLTS. So nothing more is missed. Okay. Thank you, Prince, for informing me. So how DLTS work? Actually, it's a transient measurement. We know that when we make a metal semiconductor diode, a finite capacitance due to the depletion width is present, C equal to epsilon A by T. And when we increase that bias, if you see this diagram, the first is the at V equal to 0, second is V equal to voltage equal to minus V1, means a reverse bias is applied. And if there are traps, bulk traps present in the semiconductor, here in the first diagram also it is visible in the band diagram for V equal to 0 in the middle one. In the second diagram, you see the depletion width increases, but the after a certain time is that depends the time constant of a particular time, and that trap will emit the electron. Here this n-type, so it will emit the electron. It can emit the hole also. Uh, that will be a minority carrier, and the shape of capacitance transient will be different. But here is the case of majority carrier trap. So it will emit, and in the third diagram, if you see the capacitance is increases, means the depletion width reduces due to the emission of carriers from those traps, and that is the very important phenomenon. We capture, actually we apply a pulse. You see the voltage versus time diagram. We apply a pulse at t equal to 0, a reverse bias pulse is applied, and you see the change in the capacitance. It reduces, it goes to minimum at t equal to 0, then again recovers. We measure this delta C, we measure this time, and that gives the complete information about those tabs. And this is the fundamental basic of the working of DLTS. And this is again presented the basic of how a trap is captured by a, sorry, how a carrier is captured by a trap. It can be electron, it can be a hole, it can be a majority carrier or minority carrier. So the diagram will change, but the underlying phenomena will be same. So it is an energy level in somewhere in the band gap that you can see in the band diagram. And as I mentioned in the last lecture, a charge is uh, called trapped when the capture rate is more than the emission rate. Here always we talk about the rates. It's not a constant phenomena, it's a dynamic nature, constantly emitting and capturing taking place. But statistically, when we calculate the capture rate is more than the emission rate, we say that the trap is occupied by the charge, and it has a finite capture cross section. It's like a valve that you can see this simple diagram, simple pictorial representation that how electron is getting trapped in, that is denoted by the red color. So again, how DLTS works. Earlier in the earlier slide, I explained that emission is taking place when you apply the reverse bias pulse at the metal semiconductor junction diode. Here I have shown it pictorially in a movie that when you apply a negative bias pulse, the depletion width increases, traps which are filled comes above Fermi level, and above the whichever the trap is, here it is an electron trap which is above the Fermi level, it will not keep the electron, it will emit the electron because thermodynamically it is not possible to trap the electron now. So due to that, you see the slight change, slight reduction in the depletion width that in this movie, which is in this figure animation. So that is the crux of DLTS. And when we do these measurement number of times and simultaneously change the temperature. So when we change the temperature, you see in the right side, there are different capacitances pulse have been drawn. So these trap states have a finite time constant and they freezes at a lower temperature and they emit the electron completely at a higher temperature. So when you see this timing diagram, capacitance transient diagram, the lower one diagram is a straight line in the minimum level and upper one is again a straight line but a higher level. So we always measure the difference of capacitance between T2 and T1. CT2 C capacitance at time T2 minus capacitance at time T1, and we plot the difference between the two capacitance with respect to temperature. Here, if you can see with this capacitance transient diagram, so we get a peak in the difference, and that gives us a characteristic temperature for that particular trap. So, in addition to that, what we do, we change the time constant of pulse of the applied reverse bias, and that peak of this capacitance difference shifted to the temperatures, different temperatures, and we plot this time constant of the pulse which we have given with respect to the peak shifted and the temperature. So here we get the activation energy of the trap as well as capture cross section of the trap. Nature of the trap is a majority carrier or minority carrier. In majority carrier trap, there's a dip which is a standard one. You can see is uh, obtained, but in a minority carrier trap, the capacitance reduces with time. Here capacitance increases with time, but in case of minority carrier trap because the depletion width will increase after the emission of a charge carrier from the trap, so the capacitance will reduce. So we get negative peak and we get again the same theory is applicable to calculate the activation energy, density and the capture cross section of that particular trap. So after that, in next topic, I will introduce what is the gallium arsenide high electron mobility trap. So why we call it as a high electron mobility transistor? Actually, if you talk about the MOSFET, because uh, gallium arsenide HEMT is the derivation, derivative of a MOSFET device. In MOSFET, if you see that dopants are present in the channel, so there is a impurity scattering involved, and that reduces the mobility of that electrons. So here what we do, we separate dopants from the channel, and that is the technology which was developed long back, and that has give us the freedom to design a very high mobility transistors. And in fact, gallium arsenide HEMT has the mobility of 8,000 centimeter square per volt second. It's a very high value. So if you see the Venn diagram of the gallium arsenide heterostructures, is the type 1, means aluminium gallium arsenide having a higher band gap compared to gallium arsenide. We mix, we alloy gallium arsenide with the aluminum percentage, certain aluminum percentage, normally 27%, and the band gap is increased in the similar percentage point of view. Actually, if you plot a line with the band gap between the band gap of gallium arsenide and aluminum arsenide, and you plot a straight line that gives the approximate value of the aluminum gallium arsenide band gap depending upon the concentration or alloying percentage of the aluminum. So, but there can be type 1, type 2, type 3 semiconductors. They have different applications. And then, so I will not be covering all these. So, but you can read. They have a particular applications. So after that, how this heterostructure is formed. So if you see that uh, in case of band gap, and one more thing, when we talk about the PN junction, that's a homo junction. But here, because the semiconductor material is different, we call it a heterojunction. It's a heterostructure. Uh, L gas is different material completely. So similarly, we can make other material heterostructure also, silicon germanium also. And what is the working principle is very simple. The moment you join two different band gap material, type 1 I am talking about, so there will be a discontinuity. In case of aluminum gallium arsenide and gallium arsenide, it is in the conduction band. And what free electrons which are available in the wider band gap material, they see the lower energy in the gallium arsenide, they deplete aluminum gallium arsenide and goes to the gallium arsenide, and they make a sheet charge. And that's a mobile sheet charge that we call a two-dimension electron gas. Why we call it a two-dimension electron gas 2DG? Because it has a very small thickness. Maybe in case of gallium arsenide, it's 10 nanometer or 15 nanometer, but in case of gallium nitride, it's only 3 to 4 nanometer. So, but in the other XY direction, there is a sheet. Everywhere it is present. So, by this technique, we have separated that electron, means our charge carriers or mobile carriers, from their respective uh, dopants. So, this is the practical device, how it is fabricated. There is a source drain, there is a gate, and we dope a delta. We use a delta doping. We don't dope aluminum gallium arsenide completely. We use a delta doping layer at the L gas interface, and that delta doping means a small thin layer of dopant material is completely depleted, and all electrons are transferred to that lower energy level in the gallium arsenide. That's why the conduction band is dipped at L gas interface, and we get a two-dimensional electron gas, that is 2DG. And when we put metal above this aluminum gallium arsenide surface, and a Schottky diode is formed, and by that diode we can control the conductivity of the two-dimensional electron gas, that is channel layer at that interface, and that gives a transistor action. And if you see, if we can put source or drain exactly at below the gate, that will be the ideal one, but practically it is not possible. That's why they are separated due to different issues, and we have to keep finite source, gate, and so gate drain spacings, so we get parasitic resistance value, capacitance values also, uh, that affects the performance of our this transistor. So, and this is how gallium arsenide HEMT is formed. And next is my main topic is that gallium nitride HEMT. And here in gallium arsenide, actually we have used a doping to make a channel. But in case of gallium nitride, it, we are not doping any. We are not using any doping. No dopant is used. Still we get a two-dimensional electron gas at AlGaN interface, and that too one order higher. Means in case of gallium arsenide, the electron concentration, maximum electron concentration is possible is 2 into 10 to the power 12 per centimeter square. But here it is 1 into 10 to the power 13, 10 raised to the power 13, one order higher, or it can be higher depending upon what is the aluminum concentration we are using. Sorry, actually this diagram is not completely visible, that atoms and their bond. But here I want to show that there is a aluminum gallium nitride layer above gallium nitride layer. And as I discussed earlier, this is a piezoelectric material. And when we grow aluminum gallium nitride over a gallium nitride, pseudomorphically means the lattice constant of AlGaN is followed by the AlGaN layer. Natural lattice constant of AlGaN layer is smaller than the gallium nitride, but when we grow pseudomorphically, it will follow the lattice constant of gallium nitride layer. That's why it will give rise to piezoelectric polarization in addition to the spontaneous polarization that is that is present there due to their hexagonal closed-back lattice structure and the bond ionicity present in the gallium nitride layer. So, if you see in the Venn diagram of this AlGaN-GaN heterostructure, from where the 2DAG has come, we have not dropped this AlGaN layer. We call it a barrier layer, and GaN is a channel layer. We have not dropped anything, but the theory proposed by Ibbotson is that there is a polarization charges present in the AlGaN layer, and the top surface of the aluminum gallium nitride layer is compensated by the surface trap charge present on that surface that neutralize the top polarization charges, and that give rise to electron 2DG gas, means two-dimensional electron gas at that AlGaN-GaN interface. And then you say that why gallium nitride polarization charge is not compensating that AlGaN-GaN that polarization charges. Here, we intentionally keep the gallium nitride thickness much more than the aluminum gallium nitride layer. So actually that reduces the electric field in the gallium nitride layer, and that's why we get the 2DG. And this is the main basic principle of aluminum gallium nitride HEMT. And how this 2DG concentration is related with the AlGaN barrier thickness. Actually, again, this model was presented by the Ibbotson in 2000, around 2000. When we grow this aluminum gallium nitride layer, the thickness of the aluminum gallium nitride layer increases, but the electric field inside that AlGaN layer reduces with the thickness. We know that electric field is inversely proportional to the thickness. And due to that, the surface trap which are present below the Fermi layer in the smaller thickness, they are exposed to the above Fermi layer, and they give rise to they induce the 2DG two-dimensional electron gas 2DG channel at the AlGaN-GaN interface is formed. And that's how that transistor basic operation of the transistor is achieved without any doping, but that comes at a cost, because here already we have struggled a lot in the MOSFET about this interface states, but there that interface states are not contributing any charge to the channel. They were just interfering with flow of the charge at that insulator semiconductor interface, but here they are generating the charge, and that's a big trouble. And that's why there are unique issue in this technology, and still we are not sure when it will be completely mature, but in the future I think the transistor design has to be changed, and we will achieve that complete control on this technology. So these are the DC performance now. We start our DC characterization of aluminum gallium nitride HEMTs right from the heterostructure itself. We have a mercury probe CV measurement system, means we have no need to fabricate a device to make a CV measurement. And we can calculate how charges are present, how many surface traps are present, what is their distribution, that we can do the analysis from the mercury probe CV. Here the liquid mercury is used to make dot and ring contact. The dot contact is a smaller area in the center one, and the ring contact is around 30 times area of the ring contact area. So here the working principle is very simple. There are two diodes at the surface. One has the higher capacitance, another has the lower capacitance, and in the series, lower capacitance will dominate, and we can safely neglect the capacitance from the larger one. And we are doing this measurement as a particular frequency, so we have to keep the measurement frequency as small as possible, And even we can vary the measurement frequency to see the effect how our surface traps and this 2dg electron gas is behaving with the frequency as well as with the voltage. So we can calculate what is the threshold voltage, what is the carrier concentration of two-dimensional electron gas by the technique which I have discussed in the last lecture, that how to calculate doping from the CV measurements. And we extend that technique to incorporate the effect of the traps, and we use there are two parts of the measurements. When we are measuring a capacitance, it's not a simple capacitance, always it's a combination of conductance G plus J omega C. So presence of G. So we have to remove first the DC conductance. So we have to calculate only the AC conductance, and that G by omega has the same unit of capacitance, and we compare with the C. If it is much more than the C, then capacitance value we can't use for the analysis, but G by omega values still can be used to calculate the traps, and we can calculate the energy distribution as well as the traps present, what is the density and how they are behaving with the frequency. So this is the first simple measurement we do regularly in our lab. So based upon this first measurement, after that we fabricate the device. We clean the that epitaxial layer completely. We process it. We make the device. After making the device, again there are certain issues. So to understand those issues, I am introducing a one more concept here: the virtual gate formation. Actually, at the AlGaN top surface, surface states are present. They are positively charged. They are positively charged when there is a electrical neutrality across the all surfaces. Means there is equilibrium condition, no voltage is applied, and because this positive surface charge has compensated the negative polarization charges. But the moment we apply a voltage, for example, and a gate, Schottky metal gate, nearby surface states captures the electron and become neutral again. And due to that, the negative polarization charge comes into the picture, and that lifts the conduction band near that interface at the surface, and that depletes the channel, and that is called virtual gating effect or virtual gate formation, and that is the most detrimental phenomena in this AlGaN GaN HEMT technology, because we have to make a Schottky diode. We can't avoid it. We have to make it a planar structure, because planar structure has the advantage of fabrication, scaling, and everything. That's why it is much more popular than the BJT structure. That is a vertical one. The MOSFET is more popular on the BJT one. One of the reason is the this scaling and the fabrication, ease of fabrication. So we can't do avoid that. And one more thing which we use here uh, uh, in gallium arsenide technology, which we can't use here, that is, we use a gallium arsenide highly doped layer at the top surface of the L-gas layer, but here we can't use that because gallium nitride substrates are not so available. Whatever is available in small sizes and very costly, so we use non-native substrate, just like silicon carbide, silicon, and sapphire. But this heteroepitaxy gives rise to defects. That defects propagates right from the substrate to the epi layer to the top layer of this our device geometry. That prevents us to use a highly doped layer at the top surface, and that is why our surface states are not satisfied. Either we use silicon nitride as a passivant that not passivate our surface states completely, and we get this virtual gating effect. In addition to that, we get leakage current also, because this if we have controlled the surface, we have controlled the conductivity there. So there are some finite traps which are present in the epitaxy up to the metal. They will give some uh, path to leakage, but additional path will be given by this edge effect of this metal semiconductor interface, And in practical operation, that drain voltage is much higher than this gate voltages. So most of the edge leakage current flows in the side walls of this Schottky metal gate on the drain side of the edge. So what we can do, we can use the information of this from this gate leakage currents to calculate what is the surface state distribution is. So the DIT we have calculated here is from the forward IV measurements. The forward IV measurements, what we do, we calculate ideality factor that we have discussed in last class. That ideality factor we can correlate directly with the interface density, and that gives us the surface states distribution. The moment we get the dose, we can integrate where our Fermi, we integrate to match with the 2DG available in the channel to calculate where our Fermi level lies. The moment we calculate where our Fermi level is like, we can calculate how much carriers are available and how much they are participating. So we can calculate the virtual gate lengths also, uh, what is the length of the virtual gate and how much it is contributing in the gate leakage of the aluminum gallium nitride hem. So you can see that we have plotted virtual gate length with respect to the inverse temperature. This is a straight line. That is the model we have developed in 2030. So, but again, there is some issue with the slide, Google slide. Excuse me for that. Uh, with the lower diagram, is arrows are stretched. I don't know why it has happened. So please ignore that. So, so there are the cases when you have the gate leakage is much higher, there can be much lower, or it can be intermediate that you can see here. And if you see here that in unpassivated samples means there is no silicon nitride layer at the top AlGaN surface, that leakage is very small, completely negligible. That is a desirable characteristic from the gate leakage point of view, but that desirable characteristic is not so desirable because these devices has the larger virtual gate lengths and higher current collapse values. Means current collapse is when we apply a certain electric field in the structure, the 2DG channel depleted. The moment 2DG channel is depleted, our drain current values reduces, and that's why we can't use these unpassivated samples for our transistor operation. And in the sample 2, you can see the intermediate gate leakage, and the sample 1 which is giving a higher gate leakage, that is giving a activation and some kind of thermal activation at different temperature, which was absent in other cases or negligible. So we have proposed here a model that there is an interface trap and there is a surface trap, and in sample 1 there is a surface conduction is taking place. That's why here we are getting a minimal current collapse in the drain current, but getting a higher gate leakage. And the edge effect of the gate is also present. I mean, the gate leakage current is also present, and the model uh, completely explain how this higher gate leakage is taking place with the smaller drain current collapse in these devices in this particular case. So, but if you see the off state leakage is when transistor is off, means it's reverse bias to the point when the 2DG channel is not present under the gate, but gate current is present, leakage current is present when we operate the device in the normal transistor operation. When we vary the voltage, gate voltage, uh, the current changes, or when we change the drain voltage, drain current saturates, but still the this gate leakage changes heavily with the increase in the drain voltage. So from where this is coming? So that phenomena actually we have presented that there's a multi-phonon ionization in the surface trap is taking place. That's why from there we are getting this on-state leakage currents. So this on-state leakage current has a particular peculiar characteristics, and that you can see in this diagram, that when we reduces we increase the gate voltages from negative to the positive side near the pinch off, there is a jump in the gate leakage current. Again, it reduces in the normal level. So that is due to the impact ionization in the surface traps, and that reduces our virtual gate length, and that changes our gate leakage as well as drain current, and that's why we get the recovery of the drain current due to this change in the leakage current at the higher drain voltages. And that model was developed and was presented in 2022, only last year, and that completely explained that how leakage current is behaving in the on state as well as off state, and how drain current is changing with the drain voltage as well as gate voltage. Again, Google slide, I think all texts are missing. So here in the top diagram, actually the formation of virtual gate is shown, and depletion to that virtual gate formation in the 2DG channel is shown, and the IV characteristic present in the lower side in the middle one. You can see that there is a kink in the red curve, and this is called the current collapse due to the kink present in the output IV characteristic of the AlGaN GaN HEMT. And when there is no kink, no collapse, we get the normal IV characteristics that we see in the gallium arsenide HEMT or MOSFET. This is the ideal characteristic. But ideally, we don't get that, and here we get a particular type of signature, that is a kink. And this kink is a manifestation of current collapse. If this kink is very dominant, you get the knee walkout. When this kink is minimal, you get a slight step in the output IV characteristics. So, so how this virtual gate is simulated in this uh, Silvaco Atlas simulator, as well as calibrated with the measured data. If you see that the current collapse or kink phenomena, the effect of temperature in this top right diagram, that when we reduce the temperature, that amount of kink increases. Means in the collapse region where the drain current is reduced to the negligible levels. But when if we increase the temperature, that current in the pre-kink region increases, but the current in the post-kink region where the current is recovered is reduces due to the mobility degradation to the higher temperatures. So this was the phenomena that was explained in 2013, that current collapse or this kink moves in the left side due to this self-heating effect, and the formation of virtual gate was modeled with the increase in the drain voltages, and the electric field due to this drain voltages increases the virtual gate at that top AlGaN surface. That forms a channel. Actually, if you see, try to imagine the picture in the channel. There is a N plus, N minus, N plus junction. N plus is because this is a 2DG gas, that's a very high concentration, that is N plus, and the depleted region under the virtual gate forms N minus region. So this is a diode, and this is a high resistance pocket, and the breakdown of this diode gives this current recovery, and we get this particular phenomena of the kink. But when we see this in the without self heating, means when we reduce the self heating in this devices aluminum gallium nitride HEMT, we see that kink phenomena, and that collapse point or recovery point, the changes the direction in the middle middle of the output IV characteristics. It doesn't go like this in the left side completely. At the higher gate voltages, it goes on the right side. So that is the signature of multiphonone ionization, and for that a model was developed to capture this phenomena, and we model this successfully, that how that leakage current, on state leakage current is behaving in this condition, and we successfully explain how this point is moving in the right direction. But how to explain both simultaneously? That was a challenge, and that challenge was tackled by mixing these two models. Actually, that n plus n minus n plus region is formed, but when we increase that drain voltage, the electron strikes this diode which is formed in the channel, and that gives the impact ionization. But this impact ionization is controlled one. It doesn't go infinitely or gives a breakdown, but that breakdowns the actually virtual gate, and that this is self-sustained phenomena, and due to that breakdown of virtual gate, we get the full current, and the direction of that kink or the collapse of recovery point changes the direction. That's why near the pinch off it moves to higher drain voltages. In between it goes to the lower one, and again it goes the higher drain voltages. So one more problem we have faced, that threshold voltage shift is also observed in these devices, and that too in the opposite direction. Means when we increase the temperature of a device and we see the IDVG characteristics, means drain voltages versus gate voltage, sorry, drain current versus gate voltage, the that threshold point, means where the transistor becomes on, turn on point, shifted to the right side. Ideally, actually, if there is a increase in the temperature, it should shift in the left side. Means the higher temperature gives rise to the generation of carrier normally, but here it is giving the more trapping. So why it is happening? Where is the location of trap? So we simulated again with this physics based simulator Silvaco Atlas, but here, this trap phenomena is something different. These traps have a barrier. Means the diagram which I have shown earlier, where that there was animation how charge carrier are being trapped. There was no barrier. But if there is a barrier present in the side of the valve, then electron or charge carrier will not be captured immediately. They need a certain energy, means they need a certain thermal energy to cross that barrier, and after crossing that barrier, the electron are captured, and we get this type of a particular threshold voltage shift. And then we, by the simulation and by the measurement also, by the capacitance voltage measurement also, we can calculate where is the physical location is there. The one challenge in the measurement is that because AlGaN layer is not doped, it's completely depleted, and when we applied a gate voltage, uh, either 2dc is completely present and it goes immediately within certain less than 1 volt or 500 millivolt, the complete 2dc is depleted. So we cannot differentiate whether it is at the surface or the AlGaN GaN interface, but in simulation we can simulate that it is at the AlGaN GaN interface, not at the surface under the metal, but it can be present in the side of the metal, gate metal, at the silicon nitride AlGaN interface. So again, the role of surface state in the threshold voltage shift can be present, and that we have studied, and we have simulated again this voltage threshold voltage shift from the both locations, means at the AlGaN GaN interface also and the top surface also at the silicon nitride AlGaN interface. But then you can say, then sir, what is the benefit? What is the final conclusion? So that debate and debates goes on. So my school is that because 2DG concentration mainly originated from the surface states. So most severely it will be affected from the surface states only. Bulk traps which are present near to the channel. Actually, if you talk about the dimensions, the AlGaN barrier thickness is around 22 nanometers, and there is a GaN buffer in micron thickness. And but the channel where the main channel is present is around 100 to 200 nanometer, and we try to remove each and every trap from that location, because any trap present there will reduce the reliability and deteriorate the performance drastically. So in a good design, we do not allow any good fabrication. We do not allow any defects to bulk defects to be present at that region. So, but surface stress we can't do much. We have to live with that. So my analysis is like that. So these are the DLTS results of the different aluminum gallium nitride HEMTs. So that diagram which I have shown, that in DLTS measure we get a peak in the capacitance difference, and this is the practical data. We get the different peaks, and by shifting of these peak with the temperature give us the activation energy, and we calculate the DLTS peak from the leakage current also, and they may give similar values or maybe additional peak also. But in case of current DLTS, it is not possible to differentiate between a electron and a hole trap. But in case of capacitance, it is possible. It is clearly possible. But in case of current, both signatures are mixed. But again, it's a complementary measurement. We do both. And these are again the DLTS measurements, some of the commercial devices also and our devices also, which are comparable. So from here we get to know what is the surface trap distribution, as well as what is the bulk trap distribution, what is the activation energy. uh, this is measurement gives the idea, not idea, exact values. After that, knowing that these are traps present and which type of that nature of traps also, which we can calculate. These are dislocation type, or this has a capture barrier or a point defect. Now we can give feedback to our material people, growth people, that this trap is not required or this trap is required, and the location of this trap should be the different one. So that is was a very important feedback, uh, that which is valuable not only to material people but also the fabrication people, which make the final devices. So in addition to the DLTS, we do this transconductance spectroscopy. Means we calculate the transconductance at the low VD values, and we will change the measurement temperature, and we can calculate the different traps. Here we can get deep as well as shallow trap information, but in case of DLTS, we get only deep traps. Shallow traps comes in the current DLTS. Again, it's very difficult to differentiate. So this again powerful measurement. So these are the main issues which we face in the DC characteristics of the aluminum gallium nitride HEMT, and we use different methodologies to calculate why this is behaving like that. So how this RF performance is affected is like that. When we measure this S parameters, and we calculate this gain and the unity gain frequency, we see that this is changing with the drain voltage. But in the collapse and uncollapse, there is a drastic change. So we have to calculate the amount of change the FT and gain due to the presence of current collapse, and that we have attributed the virtual gate, and virtual gate gives us this means we can quantify this FT and the gain degradation due to the collapse in the RF domain. And this is the 10 watt gallium nitride AlGaN GaN S-band power amplifier. And if you see here, the most important thing is that that gain in the red curve, the left view graph, red curve, the gain start reducing the smaller power levels. That problem is not present in gallium arsenide technology. This is the unique to the gallium nitride technology. Here the 1 dB compression. Actually, 1 dB compression is a term where non-linearity is the. Excuse me, someone mic is open. Yeah, yeah. So what I see, and gallium nitride HEMTs, that 1 dB compression comes much early. This is a contradictory. One side we are saying that gallium nitride has a wider band gap material which has a very high operating drain voltages, very high breakdown voltages compared to gallium arsenide, which gives higher power because here the 2dg concentration is one order more, as well as the breakdown voltage is one order more. So VI product is 100 times more than the gallium arsenide technologies. So we should get higher power, but we get higher power, but not in a linear one. We get non-linear effect. That is the disadvantage, and that is due to the presence of surface strains. And to design a gallium nitride or any power amplifier, what you have to do, you have to stabilize the device by using appropriate biasing circuit. You match the input uh, what we call input impedance and output impedance conjugately matched at a particular frequency from the load pull data what we get, and we fabricate the circuit, we do the measurement that gives the near to the simulated values, but the difference may arise here, just like here, that due to the thermal issues and the trapping effect. So here, what I was saying that 1 dB compression comes at the milliwatt level, but here we are getting 10 watt at the 3 dB compressions. So 3 dB compression will give a more non-linear effect, but still we can use where the application allow us. So this is the main challenge. Still we are living with this type of problem, and we are using in a different technologies, just like base stations of this mobile technologies are currently using gallium nitride technology. Why? Because nonlinearity we can filter out, but here is the one more advantage is the power added efficiency. PAE is means in gallium arsenide technologies the PAE comes around maximum around 40%, but here we can go around 70%. The 30% reduce in reduction in the power wastage give us the advantage to use this technology for different application, and thus like EV electric vehicles, this device will be the workhorse because in the lower frequency domain, in the kilohertz, we can achieve in the pulse mode more than 90% power added efficiency, and that will save the huge electricity, and not only in charging but also in discharging. So that will be the big cost saving. So in future we will see this technology will expand exponentially. Still these are the issues, there are the issues, but these issues will be solved the moment we get the native GaN substrate. That is a monothermal method of growing that. It will come because people are experimenting, and there are few companies which are growing, and the moment we get a bulk crystal substrate or native substrate, the design of this AlGaN GaN HEMT will be tweaked, and it will give a fantastic performance. So now I will tell you about the measurement which is available in our lab here. So here, if you can see the left side, it is the cryostat, liquid nitrogen cryostat. We mount devices inside that, and we vary the temperature from 80K to 450K or 500K. We have VNA, the second one, to measure the temperature dependent as parameter. We have IVCV and the temperature control of the probe station. We have RF probe stations also. And the right side there is a DLTS system. Okay, and we have CRO and custom made programs we make here. Actually, if need arises, we do the pulse measurement also. We customize our experiment suit a particular to analyze a particular problem, and for that we do the modeling also in Silvaco Atlas as well as MATLAB, and we do all the automation in Visual Basics, MATLAB, and LabVIEW. So this is the experimental setup we use here, and this is the working principle of different devices here. This is the probe station, the top left, and this how we mount the DUT and we vary the temperature. And this is lower left is the mercury probe system, and right one is the DLTS system. So this is the glimpse of our lab here. I hope you have found interesting. So this that's all. Thank you for today. I went a little bit fast, and you can ask questions now. Thank you very much.
Thank you so much, sir, from all of us from whole electronics department of IERT for your valuable time. It was really a great session. We all are very grateful that you give us a few hours from your busy schedule. If anyone have any doubt, then please ask. Raise your hand, and I will allow. Then you will ask the question from sir. Yes, Ojaswita, you can ask your doubt.
Good afternoon, sir. My
Yeah.
name is Ojaswita and I am from Electronics Branch first year. Sir, I have a question that do electrical characterization alter the properties of semiconductoring material or not?
Mm, good question. For Jaswita, actually, material is fabricated or grown at much higher temperatures. Yani growth temperatures are about around 1200 degrees centigrades, and we are measuring at the root temperature or maybe around 500 K, means 200 maximum by 200 degrees centigrade. So these temperatures are not so high to disturb the lattice of that material, but if we don't take care, that material breakdown can take place if we apply too much voltage, or electromigration can take place if we flow the high current, and just like a fuse, it can blow off. So we have to take care, we have to test in the limits, but in normal measurements nothing will happen.
Yes, Navneet, you can ask now.
Good afternoon, sir. Myself Nonit from Electronics second year. So my question is, what is the procedure of making Schottky diode on any substrate?
Yeah, actually you have to choose a particular metal first, because all metal will not be make a Schottky diode on everything. See, mercury can make Schottky diode, and in that also surface states also plays a role. But you have to choose a particular metal which has a higher work function. You deposit that metal on a semiconductor by either thermal sputtering or evaporation, means thermal evaporation or a e-beam evaporation. If melting temperature is so high, then you can use e-beam evaporation in high vacuum. You melt the material by electron beam, and you evaporate it, and it is deposited on that substrate or epitaxial layer. So that metal will behave as a Schottky. And for ohmic, you have to use different technique. But ohmic contact has to be made before the Schottky, because ohmic in ohmic we use high temperature annealing, and after Schottky we don't do that, because the moment we do high temperature annealing, we give thermal shock to our device. it will not behave like a Schottky.
Okay, Navneet, have your doubt cleared?
Yes, thank you, sir.
Okay.
Saurabh, you can ask now.
Good afternoon, sir. Myself, Saurabh Dwivedi from Electronics branch. Sir, my question is how to control the dangling bonds of the top layer of the substrate.
Yeah, very important question, Saurabh, but actually no one knows. I also don't know. We have to live with that. Whatever we are getting, we can control that performance of those dangling bond remains the same. For that, we control environment, we control our processing steps, and we try to do the multiple iterations so that performance remains the same. But as far as that silicon is concerned, we can grow native silicon dioxide that will control completely, because if you talk about MOSFET, it's completely controlled. But if you talk about AlGaN HEMT, where we are working, really, it's very difficult, and most of the times we have to live with that until unless we use some kind of metallization with some kind of conductivity at the surface. The moment we use a conducting layer at the surface, it will satisfy those dangling bonds, but it which gives rise to conductivity. And where you don't need that conductivity, it will create a problem. That's why in present technology, in aluminum gallium nitride, it is not controlled. But yes, silicon, it is completely controlled. They grow silicon dioxide in a crystal silicon dioxide that is completely saturate all dangling bond of the silicon. I hope I answered, Saurabh.
Okay, sir. Thank you, sir.
Yes, Neha, you are the next. You can ask now your question.
I would like to know that how can we use the technology in space and radio applications?
Sorry, Neha, you are not audible.
Good afternoon, sir. I wanted to ask that how can we use GaN HEMT technology in space and radio applications?
See, today also many countries have experimented by sending gallium nitride HEMT to the space. The problem here is that there is a non-native substrate, first of all. There are defects present already, and when there is a uh, radiation is on the aluminum gallium nitride HEMT, that material is robust. There is no issue with the material, but the design is prone to that radiation. The moment that radiation strike in the gate area or the silicon nitride AlGaN interface, and that disturb the space charge or surface states, that destroy our device completely. That's why we still can use for space application by degradation. Means whatever is the capability of the devices, if you use at one fourth or one third, still you can use, but that will not benefit you, because in that case gallium arsenide is a better choice. And then another thing which I explained, the moment native GaN substrate is there, and you use n plus dop layer at the top AlGaN surface, then there is a chance we have controlled surface states with ungated region, and we will control this radiation effect in the virtual gating region, and then I hope that will solve the problem. But it will take still time. Hope I answered, Neha.
Thank you so much.
Okay, Abhishek, now you can ask your query.
Good afternoon, sir.
Good afternoon, Abhishek.
Sir, my question is that what is delta doping?
Yeah, actually, that and that slide I rushed actually. Delta doping is a thing just like a delta function. What is a delta function? It is present at t equal to 0, means for a short time period. Here it is present for the short thickness, means for 2 nanometer or 3 nanometer thickness of dopants is there. So that is called delta doping. Am I clear, Abhishek?
Yes, sir. Yes. Thank you, sir.
Okay.
Good
Now,
afternoon, sir.
Satyam,
Sir, my question is this: what is the effect of surface discontinuity in MOSFET?
Actually, in MOSFET, I told you that silicon dioxide is a native oxide layer on that silicon. So that surface discontinuity is present, but that all dangling bond due to that surface discontinuities has been taken care of. If you talk about CMOS technology, there is zero defect, zero surface state, and that's why that silicon technology has progressed a lot.
Okay, okay, sir. So, sir, is there any effect on their applications in ICs or modern transistors?
Application of what?
Is there any effect on its application, like in ICs working?
If it is present, then it should have effective, but it is not present. It is completely controlled. See,
Okay,
in case of silicon, the technologies are much more advanced. Now they are using non-native oxides for these gate structures, and so they have changed the designs also. And the node technology node is there in 7 nanometer in the market. So that is a different technologies at the different level. There they are controlling the number of atoms under the gate. So that kind of precision they have achieved. Unfortunately, we are lagging much behind from those technologies.
okay, sir. And sir, one more question, sir. In two, DEC is always present in HEMT, or it will form an applying voltage or gate.
Uh, in case of AlGaN GaN HEMT, it is always present. In case of aluminum gallium arsenide HEMT, if AlGas layer is doped, either delta doped or normal doped, then it will be present without any voltage. Actually, both devices are depletion mode devices. Here, the channel is formed without applying any voltage.
Okay, okay, sir. Thank you, sir.
Okay, Abhishek.
now Satyam, if you want to ask question, then please proceed.
Hello. Hello, good
Hello.
afternoon, sir.
Good afternoon, Satyam.
Sir, my question is, sir, any delta doping effect, sir, present in ICs or transistors?
Uh,
Sir,
in gallium arsenide, uh,
what is the effect of delta doping in?
no, no, no. Delta doping is a technology. That technology is used in the gallium arsenide HAMs. These HAMs has a peculiar application, means all your mobile TR modules, means TR transmit receiver modules have this gallium arsenide HAM based amplifier. So that has a particular technology because it has a low noise, very low noise, and uh, fidelity of that transmission is very high. And in addition to this mobile, it is used in the radar communication. In DTH, your STB is having that gallium arsenide HAMT inside that. So there are plenty application, but if you talk about a particular IC or particular thing, these are silicon CMOS based, which you are talking about. In gallium arsenide, ICs are not there. Either they are amplifier or MMICs. Have am I answered your question, Satyam?
Yes, sir. Okay. Yes.
Okay.
Okay, so everyone have, I hope everybody's doubt has been cleared. If anyone has any other doubt, then please you can ask. Anyone? Okay, so good
Okay.
afternoon, sir.
Good afternoon.
Sir,
Thank you, Meta.
I have a question, sir.
Yeah.
Sir, if we want to proceed or work in microwave technology or semiconductor technology, then what are the best ways to move further?
Uh, in semiconductor, actually, you should do one course, at least one course in semiconductor physics, and for microwave, at least one course in active and passive devices. Means fundamental should be clear in terms of S parameters, and in device physics, you should be clear about the role of electrons and holes and the Venn diagrams. And in case of microwave, you have to think in dB. In case of semiconductor, you have to think in terms of exponential. So if you do these two courses, then after that you can try a simulator in your college or
क्या
wherever
बोलना
it is.
है बोलो कोई बीच में है वरना
Okay. So you can use any simulator, just like microwave office, ADS, because the student versions are available. So, and for physics base also, you can use Centaurus or Atlas. But as a microwave device engineer, you have to combine these two fields simultaneously. If you talk to me, I have a command on both fields, microwave as well as this device physics. So to master this field, you have to be graduate in two fields simultaneously. Neda, have I answered?
Yes, sir. Thank you so much, sir.
Okay.
Sir, one more question from Ojaswita. Later
Yeah.
ask.
Sir, how metal geometry is affecting the structures? I wanted to ask this.
Actually, metal geometry affects the electric field basically. If you actually that part I have not discussed. When you deposit a metal, there is a certain height also. So and a certain geometry also. It can be rectangular, it can be line, wire, or ring, dot. So main governing principle is the we have to control electric field. There should not be any edges. In semiconductor, we try to avoid edges because at the edges there is electric field crowding, and most of the breakdown takes place from the edges. So we try to avoid edges in the metal geometries. Have I answered, Ojaswita?
Yes, sir. Thank you, sir.
Okay.
Okay, sir. So, sir, our IET Society Center Head also Dr. Ram Suchit Yadav, sir, also present during this whole session. Thanks to him and Dr. Ram Suchit, sir. If you want to ask or want to communicate anything, then please you can.
Good afternoon, Professor Yadav. Hello.
Hello, Yadav sir.
हाँ हेलो हाँ बोलिए यस
जी सर, if you want to say something, please want to say something.
repeat again.
Sir, would you like to say something, sir?
I want to brief about the IET and about the presentation of the Dr. Janesh Kumar Kaushik. So let us brief about that. Huh? Okay. Now, first of all, I am very grateful to our chief patron, Professor Alok Kumar Rai, Vice Chancellor of Abdul Kalam Technical University, Lucknow, and patron Sri Vijay Viswas from IAS Divisional Commissioner Prayagraj Authority Controller IRT Prayagraj, and Chairman Dr. Bimal Mishra, who has cooperate to organize such type of lecture of Dr. Janesh Kumar Kaushik, scientist, have about the effect of deep and shallow level stripes on the DC and RF performances of aluminum, gallium, HEMTs, and I am very thankful to Dr. Joseph Kaushik. So let us brief about the IETE in brief in some words. The Institution of Electronics and Telecommunication Engineers, that is the government body and situated at the New Delhi, was founded on 2 November 1953. Today it is the leading professional society devoted to the advancement of electronics, telecommunication, information technology, computer science and engineering, and other related disciplines to these topics. So the institution has been recognized by the Government of India as a scientific and industrial research organization, and about 80,000 members are individually joined to this institute. That members are from industry, individuals, organizations from the India and abroad. Today the IT has the 64 center all over the India. One center is also spread in the Kathmandu in Nepal. So this institute is organized by the Government of India for certain objectives. The objective are this institute is the organized conferences, symposia, workshops, and brainstorming sessions involving concerned professionals, students, industry, and associated for the advancement of electronics and telecommunication engineering, information technology, computer science and engineering, and allied subjects. And this institute provide a forum for discussion on national policies and provide suitable inputs to the policy makers. It promotes the conduct basic engineering and continuing technical education programs for human resource development, and for this purpose conduct examinations and guidance classes. It promotes the use of state-of-the-art knowledge, state-of-art knowledge of the instructions. It simulates research and development in the associated discipline. It facilitates formulation and implementation of the national standards for products and services in disciplines. It enlarges membership base and provide facilities to members to update their professional skills. It brings out the quality publications for all levels of leadership. Honor outstanding professionals, and it organizes resource centers and databases. It facilitates interdisciplinary interaction with other organizations and individuals within and outside the country for the promotion of the discipline. It develops the institutions, infrastructures at various centers and expands their activities. It facilitates training and placement of IT students in various industries. It promotes IT Center of the Excellence. It undertakes society-relevant programs for upgradation of skills, particularly of physically challenged, visually challenged persons. So this institute is open for the social improvement. The students who are not getting knowledge through the institutions who are in already running. So the students who are in service period and they want to increase your career, so they can also concern with this institute. With these words, I thanks to all the members of this lecture session, and I thanks and welcome to all of you again. Thanks very much.
Thank you, sir. Thank you very much. Okay, so, sir, I would like
Thank
to
you,
call
sir, from our
Dr.
committee.
Gaurav, sir, for one more thanks.
Thank you very much. May I leave?
I would like to call Dr. Yatindra Gaurav, sir, for vote of thanks. Sir, please.
Hello, am I audible?
Yes, sir. Yes, sir.
Hello.
Yes, sir, you are audible. Please continue. Beta, please communicate again to sir.
Hello.
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 Sir, you are audible outside.
Ramsuchit sir. Hello. 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 Hello.
Dr. Yatin Gaurav sir, you are audible right now. Please continue your vote of thanks all to them.
Okay, ma'am. Thank you, sir, Ramsuchit sir, that you have accepted our this webinar under the IET organization, sir. I am very thankful to you, sir, and also be thankful. For briefing the IIT to all the students and the research scholars also, sir. Thank you, sir. Okay.